For our project, we wanted to develop an assistive robotic system that can help a patient request and obtain objects. The patient can request one of 3 objects to be picked up, including a water bottle, medicine bottle, and a food packet. Then, the rover navigates through obstacles to where the stationary robotic arm and the 3 objects are located. The arm picks up and drops off the requested object on the rover's tray. Ultimately, the rover returns back to the patient to deliver the object. Our goal is to allow for the patient to have autonomy and no contact delivery of their necessities. To execute our goal, we needed to create a robotic system that includes a rover, robotic arm, and sensors which can solve the problem of delivering a requested object to the patient. In this process, we were aiming to design a system that includes multiple threads for each one of those components. We also needed the components to work under real-time commands that the user would request. Finally, we had multiple constraints to resolve in terms of material and software to use to create our system.
In order to show how the project will look like altogether, we created a simulation of the rover using Pygame. The red block is the rover, the blue blocks are the obstacles, and the green block is the point where the rover should stop, as that's where the arm is to pick up the objects to be delivered to the user. Now let's start the simulation. Now the rover is receiving MQTT messages from the ultrasonic sensor and PixieCam. When the rover gets near the obstacle, it receives a message from the ultrasonic sensor of a distance less than or equal to 10 centimeters. This event makes the rover change direction and sends a message back with the updated direction change via MQTT. Now the rover has stopped, as it received a very high green pixel value from the PixieCam via MQTT. This event signals the arm to start using the PixieCam to pick and drop off the requested objects by the user on the rover. The drop-offs signal the rover to go back. As you can see, the rover went back faster as it didn't need messages from the ultrasonic sensor to navigate through obstacles. On the way to the arm, the rover stored its movements on the playfield by using an XY coordinate system. So now the rover can just reverse through the list of the XY movements to go back to the starting point.
This is a demo of the rover. When the rover receives a new speed command, which are 60-60 in this case, the speed rapidly grows from 0 to more than 60, which is an overshoot caused by the PID. Then the sum of error decreases and the speed also lays around 60 with an error range of 2.
For the robotic arm, when the user requests a specific object, the arm is able to retrieve that object, drop it off, and return back to its starting position.
There were several constraints for our project, including what hardware should be used, the arm and rover capabilities, method of communication between different components, and overall system design. As for the hardware, we were required to use TI-CC3220SF boards as our processors. This was met as every person on the team implemented their individual portion of the project on a separate TI board. For the arm's capabilities, we were required to use a robotic arm with 2+ DOF that costs less than $100 and can use a sensor to detect objects to pick up and drop off. In our project, we used an ARM Uno 2.0 that had a trained PixieCam to detect the 3 objects to pick and drop off. Moreover, for the rover's capabilities, we were required to use a PID algorithm for rover motor control. We were able to successfully use the PID algorithm to control the speed of each motor individually by reading the encoder values associated with each motor individually. The next constraints involved the implementation of the server, which had to be on the Raspberry Pi 3. Specifically, each TI board was required to communicate only with the server via MQTT. All our TI boards were able to successfully send messages to the server via MQTT. We used Jasmine as an existing MQTT server program and were able to have all payloads use the JSON format. As an overall system design, we were not allowed to use an overhead camera to look down upon the area of operation, and the rover had to operate on the floor of any room or hallway. This was successfully achieved as we used ultrasonic sensor to help the rover navigate through obstacles and the Pixie Cam to help the rover know where to stop and to help the arm know what objects to pick and drop off. Therefore, we conclude our project met all the constraints successfully.
To allow for the TI boards that were associated with the rover, robotic arm, and sensors to communicate with each other, we used MQTT, which is a network protocol that we downloaded on Raspberry Pi. MQTT allows for each device to subscribe and publish to various topics. This meant that the rover could publish to a topic that the arm is subscribed to in order to prompt an action. For our case, since we had to work remotely and we didn't get to combine our individual parts, we decided to create Python scripts that emulated the rest of the components. The Python scripts were publishing to a topic that our component was subscribed to. This helped us demonstrate our working component as if the other components were also connected to it.
The ultrasonic sensor uses 4 pins: ground, VCC, trigger, and echo. In order to generate the ultrasound, we use GPIO interrupts. We first set the trigger pin to high, which sends a sonic burst received in the echo pin. This is where the GPI interrupt happens, as the echo pin calculates the time in microseconds the sound wave traveled. We then convert the time to centimeters for the rover to know how far it is from hitting an obstacle. Overall, the ultrasonic sensor is important for the navigation of our rover through obstacles. It starts taking distance measurements when MQTT starts and sends a MQTT message of distance values 10 times per second. Here is an example of the rover receiving data from the ultrasonic sensor via MQTT. Here is a graph of the rover receiving data from the ultrasonic sensor via MQTT. The x-axis is the time and the y-axis is the distance the rover is from an obstacle in centimeters. As you can see, the distance measured is never 0, meaning the rover did not run into an obstacle. The distance values continuously get updated in the graph 10 times per second. In order to communicate with the PixieCam, we use I2C protocol. The I2C protocol allows us to send requests and receive responses via I2C transfer function. In our project, we use 2 PixieCam. The PixieCam is first used on the rover to read in the green pixel values the rover has in front. If the rover reads a very high green pixel value, like greater than 200 pixels, that means the rover should stop as it has reached the location of where the objects are. This event will signal the PixieCam on the arm to start picking up objects. Not only do we use the PixieCam on the rover, but also the arm. The arm's PixieCam is trained to determine object signatures for the 3 objects that need to be picked up. The data is used by the arm to pick up the requested objects by the user. After the arm picks and drops off the requested objects, this event will signal the rover to send the objects back to the user. Here is a graph of the rover receiving data from the PixieCam via MQTT. The x-axis is the time and the y-axis is the green pixel value. As you can see, the pixel value will never be greater than 255 as the range for pixels is 0 to 255. The green pixel values continuously get updated in the graph 10 times per second.
The robotic arm has 4 servos that move the arm's base, left side, right side, and the claw. By applying pulse width modulation to the servos, the degrees that they move at can be controlled using a timer. 2 threads were created just for arm control. One thread focuses on applying the pulse width modulation to the servos, whereas the second thread focuses on moving the arm to the position required currently. Since the arm has the PixieCam mounted in the front, when a command to pick up an object is sent through MQTT using a Python interface, the base of the arm rotates, and when the PixieCam finds the signature of the desired object, the base stops rotating. Then the arm uses preset positions to move to the position of that specific object to pick it up. Then it drops off the object to the tray and returns back to its stationary starting position. When another command is received to pick up an object, the base of the arm starts rotating again, and the PixieCam starts searching for the newly requested object. The weight of the PixieCam caused the arm to oscillate randomly, which was prevented by adjusting the position of the PixieCam. Overall, the arm functioned well based on the commands received and was able to successfully deliver objects despite the oscillating.
Hi, my name is Yahui Zhao, and I work on the rover part of this project. Here is an overview of how rover communicates with the MQTT server. First, I have a Python script that publishes the speed commands every 100 milliseconds. Then my rover subscribes to that message and use that value to power the motor. The rover publishes the speed readings of the encoders every 100 milliseconds to the server. It also publishes the statistic of the encoder messages that it is trying to send. Then the encoder speed messages and statistics are going to be saved in a MS Access database. Here's my code structure. I have 4 different threads. There are MQTT thread, PID control thread, motor movement thread, and SPAT encoder thread. Inside the MQTT thread, I parse the received speed command messages and store them inside the speed command message queue. PID control thread reads the desired speed values from that queue. Inside the timer callback function of my SPAT encoder thread, I read 3 encoder values and store them inside the struct called current speed value. The struct variable will then be passed to PID control thread so I can get the difference of the speed between the current and the desired, which is then applied as an input to the PID algorithm. The output speed from the PID is then converted to the actual power needed by the motor to achieve that speed goal. The required power for 3 motors are stored inside the motor power queue, and then finally, the motor movement thread reads from that queue and powers the motor UART. Here's a more detailed look of the PID algorithm. We're only applying proportional and integral. From the graph, the process variable is going to be the difference between current speed and desired speed. I time the difference by Kp and the sum of the difference by Ki. When there's a new speed command coming in, I reset the sum to 0. The set point and speed command are in unit of encoder rate, which is ticks per 100 milliseconds. The control output is going to be the motor power, so I need to map the set point to the motor power that can achieve that rate. And this is how the mapping works. I set the motor power to different constants between 0 and 127. I get the encoder reading, which represents how many ticks rotate during that time period, which is also the speed. The output speed value will then be plugged in to find the motor power based on the linear regression. And here's my simulation result. The speed command I sent, both are 60. My third motor broke, so I only have 2 of them working. At the very beginning point, you can see there is a little bit overshoot, but then the speeds are adjusted to 60 very soon. When I zoom in the plot, the graph oscillates around the desired speed. Here we have the reliability of our design system. For the robotic arm, it is able to distinguish the invalid user input and stay stationary. It is able to pick up objects when the commands are sent in a random order or mixed with invalid inputs. For the 2 PixieCams we have for our system, the first one, which is used for the robotic arm, is able to label signatures of desired objects under different lighting conditions. The second one we use for navigation is able to determine the correct green pixel value among different shades of green. For the navigation part we have for our system, it's able to detect an obstacle and stops the rover 10 centimeters in front of the obstacle. It also prevents the rover from going beyond any obstacles. As for the rover, it's able to reach the desired speed within 1 second with an error range of 2 ticks. It is also able to run for 2 days before it needs to be charged. And we have the robustness here. The robotic arm can pick up objects stably. The 2 PixieCams can distinguish the signature of the requested objects and green pixels with a 100% correctness. The ultrasonic sensor calculates the correct distance from the rover to the object. The rover receives the speed commands with no latency. If any parts fail to work or establish communication with the MQTT server, that problem would not cause failure for other parts.